Okay. Hi, everyone. I'm Vera Otiende, and I'll be speaking to agent-based simulation of contact networks and mobility patterns for COVID-19 in Kenya. Specifically, I'll give our description on how we went about simulating the epidemic spread using the, can you hear me? Okay. Using the agent-based modeling. And of course, putting a lot of emphasis on the matrices that we used to align to the agent-based modeling framework within the compartments, the demographic pyramids, and also the contact networks. So for our compartments, we had up to 7 compartments, with 2 of them being the psychological states, that's the naturally immune and the unexposed, and the others being the biological states. In the event that you actually got the disease, then you'd shift from asymptomatic and contagious to symptomatic and contagious, or directly to post-COVID immunity. Well, you're likely to die, but then we put a very small proportion there. And the ages, as you'd notice, there are more heavier ages within the asymptomatic, the symptomatic, not contagious, and post-COVID immunity. But also there's a likelihood of dying. So we took care of that. For the naturally immune, these are the agents that when they get to interact with the infection, they don't necessarily get, the pathogen doesn't get to affect them. And so they're also a small proportion. And then you also have the unexposed, those who never get to interact with the pathogen. So we present our agents as nodes. So within this particular compartment network, for us, it's important to put a lot of emphasis on the transition matrix, because we want to see how there's movement from a particular state to the other. But at the same time, there's a probability that is assigned to each of them. And that's what I was speaking to about the ages. And so, you know, that you see the faster arrows are just trying to put a lot of emphasis on the probability to rotate around that. And it's less likely to move from asymptomatic to post-COVID immunity. And also, you're likely to die, but not with a higher probability. So this takes care of both the transition and the probability. And then within the demographic and the social networks, we were also careful to take into account the age distribution. But because we are looking at the case of Kenya, the adjacency matrix was also something that was important to us. Because what are we saying here? We are saying that irrespective of which particular region you come from, because one region is adjacent to the other, then there's likelihood that that particular transect, then it's a pathway for transmission, because people get to interact across boundaries. And then we look at the layers. So the basic layer here that we considered as our primary layer was actually at the household level, where for the case of Kenya, we assumed an average of about 7 people in a household. And so within our randomization algorithm, we have cases whereby you'd find like one person living alone or multiple people living alone. And we were careful enough to ensure that we have proper representation so that we have a household held with somebody who's above 18 years, and also dependents. And so younger people who are likely students, or older people who are related to the household heads and they depend on them. So we ensured all our agents were having a primary ID, which was assigned to the household, but also looking at the other layers, we also have the school and we have the workplace. For the school, we have agents who are about 18 years old, and also those who are older. If you look at an ordinary school environment, we have teachers and other staff, and then we also have pupils. And so we are trying to simulate that as well. And so we have variations in color for the school environment there to just depict the ages. And you notice for our households, we are having different designs to represent the different categories. And for our workplace also, we have the variation in color to help us pick the different ages, and also trying to fit a few associations so that we have workplaces where there are fewer agents and also other workplaces where it's a bit compact, just to create the convenience that the infection would propagate much faster when you have many people interacting together. Of course, the emphasis around our household being the primary is because there's a lot of interaction that happens in there. And so what we assumed was that whether you leave to go to school or to work, who stay at home, and somebody leaves for school or work, they would come back home. And so if an agent gets to pick the disease or gets out to interact with people, then the household becomes the primary environment whereby the interaction of the infection would occur mostly. Yeah. And so at a higher scale, then we are trying to understand the transmission dynamics in Kenya. And we put in a few agents there proportionately to the different population sizes as of 2020 in Kenya, which was just a year after we did our population census. And so we started with about 500 agents. Yeah, and then of course we just put the direct agents, which are centroids to the central point of each of the counties. And yeah, trying to simulate how this transmission happens over 60 days. We did appreciate that movement occurs within the different states based on the transmission probabilities, but also adjacently to the different regions. Yeah, I always like looking at this because the color changes excite me. I don't know if you're feeling the kind of excitement, but I always like to look at it until it gets to 60. So Michelle, I hope you're not counting my time. There it is. Yeah. And yes, this is just like picking all the getting to have like the budgets or the aggregated amount of time. But also it was important of us to also think around assuming an intervention happened. And in this case, it's vaccination. Then you'd expect fewer people or rather fewer infections reported as compared to when there's no intervention happening. And so we picked a case example whereby let's say 40% or 20% of people are vaccinated, then you realize it takes a longer time to get to the peak of it. The delay is important for an infectious disease because then what happens, it only means that the intervention is taking place, and we realize that 40%, then 40% vaccination, then it would peak at around 38 new infections reported, and that's okay. And so that then would allow us to shift to understanding the reproduction number. Something interesting about the reproduction number, but this is something we're still simulating to see if it really makes sense. But what you were picking from here was that it gets to a point where the disease would somehow fade. And so any intervention on and off would really not make any meaning, yeah? But we're still working on this. And of course, on the mobility patterns. This is a simplistic age distribution model. It's homogeneous to work and school environment, of course, limited to social interaction dynamics. And we have lots of assumptions about work and school assignments. So those points to some of the limitations of this work. But most importantly, we were able to come up with a network for the different households and also to see how the matrices get to interact. Yes, so we're excited to see the many colors happening. There's a power team here. I want to appreciate myself, Zach, who's online. So we had Zach. Zach is a data science student at USIU Africa. He was very resourceful and also supported us with the technical work and the coding. Sami from Kemri, Mercy from SEMA, and Agnes, who's here with us. They've been such a power team supporting the formation of this work. But of course, IPM. Michelle, thank you so much. Thank you so much, Cliff. Thank you so much, Robin. Yes, that's it. Any questions? Not even about the colors? Yes.
It's a really quick question, but fantastic presentation and really important work. And I loved the little GIF where you changed all the colors for